to make your product better. My name is Joe Grand. Some people might know me as Kingpin, was my handle from back in the day. I run a company called Grand Idea Studio. Currently I do product development, come up with concepts and technologies and try to license them off to companies. I also do a lot of computer security work, portable device analysis, mobile device forensics and things like that. So kind of all over the place as far as if it has to do with physical product and hardware, I'm there. So the agenda today is pretty straightforward. We'll talk about some goals, hit some kind of high-level descriptions of security within the product development lifecycle and some classifications with that, and then we'll get right into doing the practical design solutions and look at some interesting ways we can protect ourselves. While I'm giving this talk, feel free to raise your hand and interrupt me and ask questions. Otherwise, it's probably a little better that way to have it interactive instead of me just rambling on for an hour and 15 minutes or whatever it is. Though I don't have a problem doing that. If you have a question, definitely let me know. Just out of my own curiosity, how many people here are involved in designing products, hardware-based products, or anything that requires security? A few? Okay, cool. And how many people here are just interested in like the hardware side of things and electronics and stuff? The other half. Cool, okay, good. And a little bit of incentive. I usually don't do this because it's just a cheap way to keep people here, but at the end of the talk I have one of my books to give away, which is on hardware hacking, and then we also have 3 t-shirts to give away. So if you hang around, we'll find a fun way to give this stuff out. I haven't thought about it yet though. So, all right, we'll get down to business. The goals of this presentation are also straightforward. The first thing we want to do is learn the concepts of designing secure hardware, and you really can't design secure hardware unless you understand what your threats are and understand who's attacking your product and what areas of your product you want to protect. It's just like with software-based or network securities, you can't just protect everything and assume you're okay. You need to really focus on, okay, I'm going to work on my firewall because that's where a lot of attacks are coming in, or we're using certain applications, we'll protect those. You can't just protect everything and assume you'll be fine. So what we're going to do is become familiar with the types of attacks and various types of attackers, and that way we'll be able to know which mechanisms are good to implement in our particular product. The next thing is understanding and accepting that properly implemented security is hard, and that goes for hardware, that goes for software. You guys all know that, and that's why you're at the conference. Education by demonstration is something I say in a lot of my talks, and that's basically just, instead of just standing up here and telling you things that you should believe, I have a lot of references to previous work and previous attacks that kind of prove that there is actually a threat. So, a little bit of risk assessment. I'm probably preaching to the choir here, but nothing's ever 100% secure, especially with hardware, even if it looks secure and it looks like it's really protected highly. Given enough time, resources, motivation, money, an attacker can break any system, and that goes with any hardware or software. And I just mentioned this, is you need to secure your product against specific threats. You can't just have this global envelope of implementing every single method you can, because it will get too expensive, and if you have too many security mechanisms layered up, there might be some weakness on the way in. So you need to figure out what needs to be protected, why you're protecting it, and then who you're protecting against. So this is a favorite drawing of mine, and it's a perfect example. You see this guy, this house is even more secure, front door is 4 feet thick, blah, 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 and then there's a guy climbing in through the side window. So you need to understand what you're protecting. Obviously you're going to protect, these guys are protecting their front door, but they're leaving the windows wide open. So you need to understand what and why you're protecting things. Does that make sense so far? Yeah, cool.
Why do those guys look like Pac-Man?
Why they look like Pac-Man is because the guy that drew this can't draw. It's a subliminal message that Pac-Man is evil. Okay, so looking a little bit at security in the product development lifecycle, this is similar if you've ever worked on software applications and application development. It's trying to get security into a product is really hard to do, and it's hard to convince management, it's hard to convince people that needs to be done. However, in order to have proper security, it needs to be done while the application is being developed. You can't retrofit security later and hope that it's going to work, because it usually never does. So the first thing is establish a security policy as the foundation, as the base of your design. With hardware especially, you can't have a secure product or any applications running securely on hardware if the hardware is not secure. treat security as an integral part of your system design, meaning you need to constantly look at it, constantly revisit security as you're working on your product. If you make changes to your circuitry, to your firmware, you need to reanalyze and make sure that the device is still as secure as you want. Because if you introduce a bug, you might then introduce a way for an attacker to get into your system. Reduce risk to an acceptable level. I mentioned this again, elimination of all risk isn't cost effective. You can't protect against everything and still have a product that's financially feasible to sell, unless maybe you're military or government or somebody. But for the most part, if you have a consumer device or you have something, you can't protect against everything. And the other thing is, the last thing here is put your eggs all in one basket. Minimize the system elements to be trusted. That basically means if you know what areas you want to protect, try to keep them all in one region, and then you can focus specifically on protecting that. So say you have your processor, your flash ROM, and like some SRAM, and you have crypto keys stored in flash, or you have some IP and firmware that you want to protect. So those three components are kind of like your digital area there that are really critical. Put all those in one area, and then use mechanisms to protect those. Even though the attacker will go right to that area because they'll say, okay, it's protected, so something must be good there. At least you can focus your efforts on making sure, instead of trying to use one security mechanism to protect flash, one other thing to protect the processor in a different area of the board and whatever. So put all your eggs in one basket, and that's kind of the opposite of what a lot of people hear with network stuff is separate everything so it makes it harder. In hardware, that's not the case. So a little bit more, strive for simplicity. Keep your hardware mechanisms as simple as possible. If you start layering things up, and if you have complex security that hasn't been tested properly, you might be introducing some more problems there that might be discovered later on. Implement layered security, I already mentioned. And then don't implement unnecessary security mechanisms. This is something I see a lot because management says, let's implement X product because our competitor uses it. This was something I saw back when I worked for an unnamed security consulting firm a few years ago that I happened to be a co-founder of. Our CTO came to us and said, our clients are all using Microsoft Outlook and Exchange. How come we aren't? So it's the same type of thing. We held off for a while and didn't use it, and then eventually we kind of gave in to the man and set it up. So the same thing is don't implement mechanisms unless you need them. Don't just do it because a client wants it or because a manager wants it who might not understand the global scope of things. So only implement security if you need it to define a goal, or if you need it to support a defined goal. So looking a little bit at kind of like the academic view of attackers, there's three different attack types for hardware that I've kind of classified here. The first is an insider attack, and that goes for hardware as well as network and software-based attacks. That's the most percentage of attacks and of breaches are from insiders, whether they're disgruntled employees or they're through your product manufacturer in Asia, in Mexico, creating additional units of a product that you would only authorize for a fixed amount. So this is really common. A lot of times with pirated hardware in Asia is somebody in the United States will work with this manufacturer and say, okay, we want 100,000 units to be delivered to us. The manufacturer will give 100,000 units back to the client, make another 50,000 to sell inside of Asia, and the laws are so different between all of the different countries that it's really impossible to do anything. So that's an attack that if you have specialized intellectual property or firmware that you need to protect, there's steps there you need to protect against. Lunchtime attack is another popular one. That's like a 15-minute, half an hour type of attack, maybe during a coffee break or lunch. Basically, an attack would take place during a small window of opportunity if you leave your authentication token on your desk while you go to the bathroom, or you leave your PDA sitting on your desk when you go get lunch, or you check your coat when you're out to lunch somewhere. An attacker could get access to that through the coat check and do whatever they need to do with your hardware. And then you have the focus attack, which is basically everything else. It's people that are highly dedicated, time, money, resources either aren't an issue, or it might be an academic type of thing, or it's some grad students or some college students that have access to all the various hardware that they can use to attack your product. And their real goal is to break it no matter what, because their grade depends on it. So a little more classification here. You'll see we mentioned these a little bit, and this is actually based off off of an old classification by some guys at IBM back in like the late 80s or early 80s that there's a reference to in the back. We have three different classes. Clever outsiders are like the curious kids. I wouldn't necessarily call them script kiddies, but it's people that will try to take advantage of an already known weakness. You know, they won't necessarily come up with their own attack against the product. They're smart, but they might not understand what the attack is about. Class 2 knowledgeable insiders, those are more of the technical people. They have the tools available for themselves. They know how to use them. They create their own types of attacks. And then you have funded organizations, military, government, Microsoft, whoever you want to put in there. People backed with a lot of money with the main goal of defeating a product, no holds barred. And they have access to the tools. They have the thousands, the tens of thousands of dollars to outsource reverse engineering and other things that they need to do. So another way to look at it is through a table. So you basically have the class 1, the curious hacker. You know, their time is limited. They have a limited budget. Creativity varies. The goal is probably one of the most important parts of this table is why the attackers are attacking the product. For most people, it's just the challenge of doing it, and that's the curiosity factor. There's a lot of them. They're not organized, and they might release information in the form of an advisory or something else. Academic, I mentioned them before. Their target goal is publicity because that's what academics do, is release their information and get more famous. Sorry to anybody who's out there, but that's my view of it anyway. So they have access to a lot of resources, and they want to get famous and show their smart work. Class 3, we have organized crime and government listed here, but you can see their goals. Organized crime is always money. Government, it's hard to tell. You don't know how many there are, but both of those groups are highly organized. And their methods of attack are way different, I think, than the Class 1 and Class 2. So most of what we talk about here will protect against Class 1 and Class 2 if implemented properly, I'd say. Class 3, you run into problems where it really gets difficult if somebody's determined enough. And then we look at this is instead of looking at the attacker, it's looking at classes of the difficulty of attack. So this is something if you wanted to classify your product in a way that you had to show management or show somebody how secure your product was. A chart like this, something similar to this is common in the safe industry, in the physical security industry. It's like how long does it take somebody to break into this safe with these certain tools. So it's the same type of thing here. You go from no tools that you can attack the product by accident, which is possible, or you just have common simple tools, and all the way up to the in-laboratory types of things where there's only a few places that actually have the resources available. Expensive X-ray equipment, rework equipment, and failure analysis types of equipment. So there's a large range there as well. Any questions so far? No? Cool. So there's 4 different ways that an attacker can gain access to your product, and this will vary depending on what your product is, obviously. The first thing is they can just purchase the product from a retail outlet in cash if they want to stay covert. They'll own the product, they can bring it back to their lab, do whatever they want with it, with basically no risk of detection at all. A lot of times with an attack where somebody purchases a product, they'll purchase more than one, use a few as guinea pigs or as sacrificial lambs to open the product and see what sort of security mechanisms there are, basically destroying the product in the process. But then they'll have one unit that now they know where the security things are, they can go and defeat those. So if you have a consumer product, a retail product, that's probably what will happen. Another thing is evaluation. So for network equipment and maybe more expensive types of tools, the attacker wouldn't have the cash or the funds to straight out and buy the product. They could rent it from a number of places or borrow it. The problem there is that, at least for an attacker, they're going to be less likely to really do any sort of physical tampering of the device because if they return it, it's going to be obvious that it was tampered with. So they'll be a little more careful there. An active attack is as it sounds, when the product's in active operation, like a router, like any sort of network equipment, something that's constantly running, and the attacker is attacking the product at that time. Also, they don't own the product. So that could be a cell phone, or that could be something like a lunchtime attack, like a PDA, or or an authentication token or something like that, that's in active use, and they really, the threat levels kind of change there. And then remote access is the final one, where the attacker doesn't have physical access, again, network equipment, things like that, where they're launching all the attacks remotely. So those are the four ways that seem to be popular. A little more classification stuff here. There's a few different threats and reasons why somebody would want to attack a product, or at least how they'd attack your product at a really high level. You have interception or eavesdropping. That's basically retrieving data or accessing data without physically opening the product, and we'll get into ways to do that. Interruption, fault generation, that's preventing the product from functioning normally, whether you're injecting certain voltages or you're injecting RF, or doing something to have it try to fail in some sort of unintentional manner. Modifications, the next one is physically tampering with the product. It's usually invasive, meaning the attacker would open up the product, get to the circuit board, maybe change things around to do what they want it to do, or to retrieve the data they want to retrieve. And then fabrication is creating something, a counterfeit asset, so a counterfeit piece of data of a product. That might be for cloning purposes of an authentication token, or a man-in-the-middle type of attack. And then I think this is our final classification slide. Attack goals. The high-level reasons of why somebody would want to attack your product, there's obviously more, but these are kind of the four that I've seen as the most important. The first one is competition and cloning, and I talked about that with the run-on fraud. Somebody wants to gain a specific piece of IP, a specific piece of firmware, an algorithm, your encoding routines, your crypto keys, or whatever, specific IP theft to gain a marketplace advantage. So that would be, if you're a manufacturer in Asia and you have somebody's IP, you can create their whole product. So competition's a big one. Theft of service, obviously a popular one for a lot of people. Think of cable TV boxes, think of cell phones. Anything obtaining service that normally requires money, people are going to want to break. User authentication, spoofing, that's smart cards, authentication tokens, becoming somebody trying to prove you are who you say you are type of thing. Forging a user's identity to gain access to a system, or some sort of other resource. And then privilege escalation, gaining root, so to speak, or feature unlocking, getting access to undocumented features, or features that might not be intended for commercial users, but might be for developers. And you see a lot of that, sometimes they're called Easter eggs, inside of cell phones and inside of various other devices. All right, now we get to fun stuff. You guys good?
Where would you put something where you're trying to get competitive advantage, where you go through and you're a competitor, you look at the other competitor's product to try to find vulnerabilities, so that in essence, while they're trying to fix their vulnerabilities, you go off and get beyond them. You're able to market your product, which doesn't have a vulnerability, and you're able to outsell them, and then therefore they're relegated to smaller sales than they would normally be.
Right, so that would be like a company reverse engineering a product, a similar competing product, to find out what the other vendors' vulnerabilities are, fix them in their own product, and then release that.
Yes.
Where would that fall under attack goals? Would probably be competition or cloning. Oh, for threat vectors? Well, the threat vectors are really how they're attacking the product. So it might be a combination. They might intercept data, whether they're monitoring RF emissions from the device. Most likely it will be a modification type of thing. If they're looking at circuitry and they're reading memory and figuring out how they're reverse engineering the circuit board, analyzing things. So the threat vectors are the possible definitions of attacks at a high level, and then the goals are really why somebody would want to do it. So yeah, it would be, this depends on what attack you're following through on. Does that make any sense at all? A little bit? Okay. Well, we'll keep going with some of the solutions, and then that might answer your question. Anything else? Okay. So now we'll get into some of the actual design solutions for secure hardware and things you can do to actually protect yourself. And we'll look at 3 different layers and kind of peel them back like an onion. So we'll start with the enclosure level, so the physical design. Then we'll get into the circuit board level, circuitry level, and then look at some firmware things you can do to protect yourself. In a lot of these examples, unfortunately, a lot of the things we talk about, there aren't easy ways to fix yourself. So that's why you really need to weigh the risk and see which things you need to focus on. Because secure hardware in the industry, or at least in the product space, it's been researched a lot in the academic area for probably 20 or 30 years, but actually implementing the academic research into products is a lot harder. So a lot of this might sound like doom and gloom, as you'll see. So for product enclosure, the screen's really bad. I apologize for that.
I think it's on your end.
My screen looks great. Well, we'll see. It's good over here. Anyway, with product enclosure, basically what you want to do is protect easy access to the internals, and that makes sense. The harder it is for an attacker to open your product, the harder it's going to be, for the most part, for them to attack your product. There's two different pictures here. The first one is just opening up an iPod, which you can do with either a screwdriver or a little plastic wedge, carefully right around the edge, and open it up. This is actually one of the hacks in the hardware hacking book, so if you're into that, stay tuned till the end. And then this other one is an old attack I've done on some authentication tokens, and I get into this in another talk later today. Just using the X-Acto knife to basically get access to the circuitry. In this case, I could do everything I needed to do, put it back in the case, reglue it, and I was all set. So if the case was harder to open, or it might have left some sort of physical evidence that I had tried to get in, then the attack would have been a lot harder. So as far as enclosure, we'll look at three different areas that are pretty important. One is external interfaces, any connections to the outside world, tamper mechanisms. These should actually be called anti-tamper mechanisms, and then emissions and immunity. So external interfaces are products lifeline to the outside world, whether it's a serial port for a PDA, like a hot sync port, whether it's for programming or for manufacturing testing, which you see a lot of. That's really one of the ways that the manufacturer, that a user will get access to the product. So there's a bunch of different examples. RS-232 JTAG is one that we get into a little bit. I like that one a lot. So here are just two different examples. Here's one picture of a particular time-based hardware token that I looked at a little while ago. And you can see right here, right behind the sticker, there's 5 little dots, and those are test points that were actually used for some sort of manufacturing or some sort of programming scheme. So that would be an attack vector for somebody right away. Looking at a product, you peel back the sticker and say, okay, if there's pins that are accessible to the manufacturer, they must be important for something. I'm going to try to attack that first. So that's like a big red flag. And the same thing here is another product, an old version of a two-way pager that had some test points down here on the circuit board, and then on their housing they also had the holes drilled out that were covered by a sticker. So if you removed the sticker, you had access to the holes, and then you could try to attempt an attack that way by reverse engineering. So suggestions here, obviously, don't just obfuscate the interface. If you do need an external interface for your JTAG or for your manufacturing or bed of nails or whatever, don't just try to hide it, because as probably everybody here knows, security through obscurity doesn't work. Hiding things doesn't work because it only takes one person to discover where it's hidden, and then everybody knows about it. So examples of obfuscation using the hidden access doors or stickers or proprietary connector types, things like that are big red flags, and it's where an attacker will go to look first. So if you need one, you either have to bear that risk of having them there or figure out a way to do your assembly or your manufacturing without requiring the pins to get the outside world there. Which usually just involves changing the manufacturing process. If it's, if you're using those pins for testing or for programming, just make sure you do everything first and then button up the case. Or don't even have them in there at all. So this goes along with it, is removing JTAG and any other diagnostic functionality. JTAG is a serial interface that's used for chip testing and board level testing of devices. It's basically it's a wide open, totally unprotected interface that's used for manufacturing. Basically, you can send serial streams of data to a JTAG port on a processor or on another type of device and get access to all of the pins and probe the device. And since you have access to the pins, you can probe devices that are connected to those. It's extremely useful for manufacturing and it's excellent, but for a security point of view, it's totally ridiculous to have it there. There are some some links in the back. Bunny Huang, who wrote the Xbox book, has done some research with JTAG. Some guys, XDA developers, xda-developers.org, I think there's a link in the back, have done a lot with an XDA device, which is a Pocket PC device, that they discovered where the JTAG port was. It wasn't physically accessible to the back, but they found out where it was by probing the board, and then were able to load various versions of firmware onto that. A lot of other devices, people are using JTAG to load Linux on instead of, the stock operating system. So it's a wide open backdoor that a lot of attackers are using. So in that case, it's hard to get rid of, right? Because if it's a module in a processor on a die, there's really not a lot you can do to get rid of it other than not having it there in the first place, or physically destroying it. Because if you're just cutting traces or blowing fuses to prevent the port from being used after you use it, an attacker could go in and then repair those ports and then use it. So
what's the solution? I mean, you got an expensive product here, and you build for manufacturability and also for failures and being able to repair them.
Right.
And then what happened in security, you'd be throwing the box away or throwing the circuit board away, and that could be an expensive solution.
Right. Well, the question is, what's the solution in that case? Because if you have a product that's designed for manufacturability, what are you going to do? And that's the problem, is if you're designing so much for manufacturability, anything a manufacturer can do, an attacker can do. So you need to figure out a way to either, if you're programming chips, for example, you wouldn't program them through JTAG, you'd program them individually in a device programmer and a gang programmer, put those on the board, and then use some physical protection methods, which we'll look at, to protect those. Having any sort of serial interface there, an attacker can just, throw together a JTAG interface with a couple dollars worth of parts.
But then if the chip goes bad or if the fails right there, then you put a tamper-resistant feature around it, you throw away the board.
And then in that case, if the chip goes bad or you need to do some sort of RMA or some sort of debug on the product, then you're in trouble because you can't get access to the part. And that's another one of the security trade-offs, is how much do you want convenience versus security, and how much money. And there's some companies I've dealt with have basically acknowledged the fact that when they're using certain protection methods, once those are out, the only thing they're going to do if it breaks is just send out a new one. And that's just part of their cost. And that's, it's worth spending the extra $500 to give the client a new product than bear the risk of having somebody attack the product and completely rip it wide open. So you need to weigh that risk. Another thing is if you're designing your own devices or your own silicon dies, or you're working with a company that will give you a custom die, is request that the JTAG interface isn't there. Request that any sort of diagnostic interfaces that you don't need aren't put in. And just limit the amount of available resources that are needed for manufacturing, and then you limit the amount of available resources that are there for an attacker. I mean, there's no easy way to do it, and that's like an ongoing thing. Another thing I've come up with that might work is to create some sort of, encrypted JTAG, where you have encryption done on the die and then you have encryption done in your JTAG hardware that will communicate. But then you'll see there's attacks at the die level of chips that an attacker could just go and bypass the encryption routines and get right down to the JTAG module. It's basically the Achilles heel of any hardware. It's scary as hell, but it's something that you need to know about. Because a lot of manufacturers don't even know that JTAG is a problem, and they'll just design, they'll use it for manufacturing. It's great. They'll program their devices, they'll test their devices, release it, and then they wonder why they got owned. They wonder why people are using their products to control robots or to run Linux or whatever. So it definitely comes down to like a risk management thing. So a little more with external interfaces aside from JTAG is any other interfaces, whether your serial, USB, even a custom interface there. Protect against malformed packets, intentionally bad packets that somebody might try to send to cause some sort of problems or failure on your device. Another thing, if you are sending any sort of critical information over an external interface, whether it's passwords or any sort of other thing, you might not want to do that. If you don't have to, don't do it. Only publicly known information should be passed, because somebody can monitor those lines. If there's data going to the outside world, somebody could figure out what it is. For example, with the Palm OS operating system for PDAs, there's some research I did a few years ago. Basically, their system password is encoded and sent over the wire when you're doing a hot sync transaction. It's sent to the desktop. That way, when you're looking at your private records, the desktop will say, oh, this is a private record, and then prompt you for your password. You have to enter in your password. It will encrypt it or encode it, compare it to what it has from the Palm device, and then it will know if you have the correct password. In this case, all an attacker has to do is spoof a hot-sync transaction long enough to get the encoded password, run some of the tools I created to decode the password because it's just some XORs against a constant block, and then you have the password of the user's device. So if you have to, at least use proper crypto if you are transmitting things. Wireless interfaces we don't touch on here. There are obviously external interfaces because they communicate with the outside world. As you know, 802.11, Bluetooth, they all have risks. It goes a little bit beyond the talk, but if you are using wireless interfaces, research the areas and research any problems with the interfaces that you're using. So, tamper mechanisms, that's it for external interfaces. Tamper mechanisms is kind of like the meat of this talk. Basically, as I said, they're anti-tamper mechanisms, but I'm just going to call them tamper mechanisms because that's my habit. And basically, they're mechanisms used to protect against tampering, hence the anti-tampering. Basically, they're physical security methods used for a number of reasons to prevent against physical or electronic attacks against your product. And it's broken down into 4 different sections. One is tamper resistance, one is tamper evidence, one's tamper detection, and one's tamper response. And they're pretty self-explanatory. Resistance is going to physically try to prevent an attacker from getting access. Tamper evidence is some sort of a physically evident or visually evident sort of thing that occurs when somebody attacks your product. Say, we get into some examples of that. Detection is a sensor or something that will detect an attack, and then response is the responsive action that will take after an attack has been detected. So, most effectively used in layers. Layering of any sort of security mechanisms is good as long as you don't layer too many and as long as you understand what you're doing, as we mentioned before, and you're focused on all your eggs in one basket. You're focused on securing one particular area. The problem is a lot of the current tamper mechanisms or anti-tamper mechanisms can be bypassed if you know the knowledge, if you know the method. So that way if somebody does purchase a bunch of your products, opens a few up to figure out, okay, they use some epoxy here, they use some sensors here, there'll be ways for an attacker to get around that. So when you're designing anti-tamper mechanisms into your device, you really need to make it sufficiently hard enough, whereas the information that the attacker gets is worth less than all of the effort that they had to put into it. That way, if somebody's attacking your product for money or some sort of other thing, it's not even worth it. For a curious kid, they might not care what they get as long as they're just attacking your product anyway. So another reference to a paper here provides a bunch of interesting attacks and countermeasures against all sorts of various tamper mechanism devices, and we'll get into a few of these. So the first one is tamper resistance, and that's basically using materials to make the tampering more difficult to resist the attack. So examples here are using some hardened steel enclosures, temperature hardened, special locks. A good byproduct of tamper resistant types of things are that they're tamper evident, meaning if you have something that's really hard to open, like steel, and somebody's trying to cut through it or whatever, you're going to know right away that somebody's been attacking your product. The problem is a lot of the tamper resistance features are hard to do on portable products and on low cost types of product because you're obviously not going to use steel or specialized locks or anything for a low cost product. So a little bit more on the tamper resistance, using security bits or one-way screws, something that just makes it either sufficiently difficult to get in or just outright a pain in the ass to open your device. The thing with security bits, which are the specialized heads, specialized screw heads, they can still be bypassed, but it does raise difficulty over a standard screw or over Torx. So if somebody was attacking your product, they need to plan beforehand to obtain equipment in order to open the device. One-way screws are a little bit better. Those are the types of screws where you can screw in one way, but opening them's harder, like on all the bathroom stalls. The thing with those is that an attacker could just drill them out, drill the heads right out, and pull them out. That's a more destructive attack, and it's going to be obvious at that point, unless the attacker happens to have another set of one-way screws that they can put back in afterwards. Encapsulation, this is a fun topic for me. Basically, encapsulation is used to prevent prevent a circuit board or prevent certain components against moisture and dust and things getting into your circuitry and possibly causing some havoc, which is usually an epoxy or urethane coating covered over critical parts. The problem is that encapsulation isn't designed specifically for security, but you can make it difficult, sufficiently difficult anyway, for an attacker to remove, at least in a way that it's not totally obvious. So one example here, though, is, and I might even have, I don't unfortunately have a picture of it at this point. Later on in the talk I do of encapsulation, but there are ways you can use chemical solvents, and you can use a Dremel tool with a wooden skewer I discovered to get access to remove some of the epoxy encapsulation. But that's something that if you have encapsulate on a product, that's not going to be a lunchtime attack. So if your goal is to prevent against lunchtime attacks, you can use encapsulation. If you're trying to protect against somebody that has an unlimited amount of time, encapsulation might not be good because they can sit in their lab for 4 hours with a Dremel tool trying to scrape it all off. So there again, you have to weigh your risk and understand what you're protecting against. A little bit more on the tamper resistance. Using sealed or molded housings for certain products can come in quite handy. Like with the first example I showed you with the authentication token, using the X-Acto knife to open it up, that housing wasn't sealed. It was a two-piece housing, so I could easily just cut the glue right open. The picture in this case is another USB token that has a sealed housing. And in my talk later on, I'll show you what happens when I try to open this. But you can't just take an X-Acto knife, an attacker can't just simply open the device. So right away, you get rid of the lunchtime attack. It's tamper resistant, and it's also obviously tamper evident. If somebody's trying to open the device, you're going to know. So using ultrasonic welding, high temperature glue is another thing that people have used instead of completely sealing the housings. The only problem with that, if you do have a two-piece enclosure with high temperature glue, you need to make sure that the glue melts after your plastic of the housing or after your material of the housing. That way, if somebody's trying to use a hot glue gun to soften up the glue, they're going to melt the enclosure before they melt the glue, and then you have some tamper evidence as well. It'll be obvious that somebody's messed with it. So this goes without saying, if you've implemented the sealed housing properly, you're going to physically have to destroy the enclosure to open it. And if you come to my talk later on today, I think it's at 4:45 on the authentication token stuff, you'll see what this thing looks like after I hit it with a Dremel tool. So the problem here, again, consider your service issues. If you have a product that needs to be serviced on a constant basis, or if you want to do failure analysis or something and then return that exact product to somebody, it might be harder to do, because if a legitimate user can open the device, like your RMA people, like your failure analysis people, so can an attacker. So you need to figure that out. Tamper evidence is the next thing, and that's basically leaving any sort of visible evidence, making it obvious that a tampering event has occurred. The good thing about this is it's a major deterrent for a lot of people, especially for the minimal risk takers, curious people that might want to look at a product, but if it's their $300 iPod, they're curious, but they don't really want to break their product, so if you have some tamper evidence there, they might not want to do it. A good thing with tamper evidence, if you implement it, and you have a product that people can rent, as we mentioned, or borrow from somebody, if you implement certain features, attackers aren't going to want to really mess with it if they notice that there's tamper evident features, because then it will be obvious that they've tried to do something sneaky. So the only problem with tamper evident features now is it's only successful if there's a process in place to check if there's been an attack. So if an attacker purchases the product, having just a visible evidence of tampering isn't going to do any good if nobody's standing over them saying, hey, you just tampered with my product. In certain cases, maybe in a security environment, if you have PDAs or if you have some sort of authentication token again, there might be a process when you go onto your base or when you go into your corporate environment, somebody's there to check. Just like they'll check your ID at the door, they'll check, make sure your hardware hasn't been tampered with. There needs to be a process, otherwise it's totally useless. So some examples of some of the tamper evident features, using special finishes on enclosures is possible. They're a little bit expensive, but you could use brittle packages, meaning things that will break or crack easily, leaving obvious marks. Crazed aluminum is a cool one. That's basically aluminum with all sorts of various intentional cracks on it, and all of the cracks are basically random, so it's like having a fingerprint of each device, like a unique identifier. So if those cracks change, it's obvious that somebody had touched it in a way that shouldn't be. And then bleeding paint's another one where you have a certain color of paint embedded with little tiny globules, I guess, of another color, of a contrasting color, and if somebody scratches the paint or pokes the paint, the other bubbles will pop, and then you'll have this contrasting color. You also have passive detectors that are more common. Some security seals or tapes that are used over a screw hole. You've probably seen them on the back of a lot of devices, void, your warranty is void if you remove the sticker or if you access this screw or whatever, and most times you don't care, but if it's a security product and there's a policy in place, that might come in useful. The only thing is that a lot of the security seals that are in existence can be bypassed, so there's your doom and gloom scenario. Which is why you need to layer that with other security features, because by itself, it might not be that good, but with some other tamper mechanism features, it will be good. So there is a reference to a paper there. Tamper detection is the third of the four parts of tamper mechanisms, and that's enabling the hardware device to be aware of tampering. So that's using sensors and using switches to say, hey, the hardware will say, hey, somebody just tried to open me. I wasn't supposed to be opened. Somebody tried to send me a packet that I wasn't supposed to receive. So for physical things, you have the switches that will detect if there's been a breach of a defined security boundary or just simply opening the device, moving a component a certain way. Various switches to do that. Also sensors, which would detect against any sort of environmental change. Temperature and power are popular attacks. Probing with X-rays or focused ion beams is something that's more of an advanced attack, and I think we mentioned that later. But if you have sensors in place, you'll know that an attack has been done. So down here is kind of a funny example of, this is an old expansion board for, oh, that's bad. I think it's something from Miss Pac-Man. I looked at my notes, but that would take too long. So it's an expansion board that Midway came out for one of the arcade games. I'm pretty sure it was Miss Pac-Man, that the arcade operator would plug into their unit, and it would give them new games so they could use the rest of their hardware in the same way and just plug in this module. So 20 years after this came out, a guy had tried to open it up and reverse engineer it so he could create a PC-based emulator for it. The first thing he did was take it to the vet where he worked and x-ray the device. So with x-ray, he could figure out, okay, here's the processor, here's some address logic, and basically figure out at least from a high level what it was doing and try to figure out by the pins and by the way the traces were connected what these logic things were. It turns out that this device was just basically encoding some of the address lines and flipping address lines around. So he reverse engineered that just using an x-ray. For critical applications, if you have an x-ray sensor in there or some sort of sensor to detect that x-ray or some sort of radiation was penetrating the device, it could then respond on that, and that gets into the tamper response stuff that we look at. Some other tamper detection of a circuitry level is to use a special material wrapped around critical areas of circuitry, creating a defined security perimeter, security envelope that would detect a puncture, a break, any modification of that. You could use some flex circuitry that are common for interconnects between circuit boards. Nichrome wire, which will change resistance as the length is changed, or as its orientation is changed around. Fiber optics, where you could have a sensor measuring light power, and as you change your fiber optics, the light power might change a little bit. And then the coolest one, which I haven't done a lot of research in yet, is a company called W.L. Gore came out with something called the D3 Electronic Security Enclosure. And that's basically this thing that you wrap around a product, like an envelope, and you wrap it around a product that's basically, they say it's impermeable to x-ray, so somebody won't be able to x-ray the devices underneath the envelope. You can't puncture it. There's some crisscrossed wires in there, so you can't drill through it. It's too fine pitched. They have some interesting security features in there. So you can wrap that around a product that will connect to a battery and some other things, so you can do some tamper response based on the detection. But again, it would be something that would be definitely worth investigating further. So tamper response are the countermeasures taken upon the detection of tampering. So you have your tamper detection features, you have your sensors. If something happens, now you have your tamper response. Otherwise, it doesn't really do much good to know an attack's taking place and not doing anything about it, unless you have a honeypot or something like that, where you're intentionally trying to get people to attack your product. So it works hand in hand with tamper detection mechanisms. One of the most common things is to erase critical portions of memory when an attack is detected, or just removing power from the device. So erasing memory is called zeroizing. So if you have crypto keys stored in memory, you have something that you want to get rid of right away, you can do that. You know, if a detection's, or if a tamper's been detected, you erase your memory and you should be okay. The only problem is that for most types of memory devices, the contents of memory aren't completely erased. So there's another doom and gloom scenario, is you're kind of doing the right thing here by trying to erase memory, but then you have these technical constraints of the physical device that is not being completely removed. And Peter Gutmann wrote an excellent paper on some of the information, or some of the data on how volatile memory retains information. So there are some solutions there. You can say, if you have a crypto key, you move the key around in memory so it doesn't create this burn-in effect like you have on a monitor, because that's what happens a lot of times. So if you move the key around enough, then you can properly erase that. So again, it's understanding the protection method and it's understanding what you're trying to protect against. Some more tamper response features. Shutting down or disabling the device, depending on your device. If it's a cell phone, say, if it detects that somebody's trying to clone the device, change the IMEI or whatever, it can shut itself down, disable itself, maybe forever, or maybe until somebody at the cellular provider re-enables the device in some way. One kind of funny solution obviously isn't good for just about any application, but for military and government, I wouldn't be surprised if they use this, is having some sort of physical destruction. You know, this message will self-destruct in 10 seconds. If a tamper event's been detected, it'll use a small shaped charge or whatever and just totally physically blow away whatever circuitry somebody was trying to look at. I wouldn't be surprised if that's used. I don't have any first-hand experience, but it is a kind of cool idea. So another thing is logging mechanisms, and this is sort of not really a physical response other than just providing a log of what's going on, just like you'd set up logging for like forensic readiness types of things on your servers, on your systems. One response might be to just enable logging, which will help later for forensic analysis, but it also might help you gain an idea of what the attacker is trying to do to your product. So logging mechanisms probably won't be good if you have a consumer device that somebody just bought at a store, but if you have a network appliance or you have something something that's an active operation and somebody's trying to attack, using logging might be good. You need to make sure though that when you're implementing the tamper response features that you keep accidental triggers to a minimum, which means in certain cases the end user might need to understand what environmental conditions they can operate the device under. So if it's in a military environment, they have to say keep it within these temperature ranges or operate under these conditions.
Especially with the use of shape charges.
Especially with the use of shape charges, right? It's like don't try to microwave your device type of thing. So don't attack it. But so that might be the case in certain situations. So the next part of the enclosure and housing level things is emissions and immunity. And this is basically all electronic devices generate EMI, electromagnetic interference, which are emissions from the board, RF noise, things like that. I don't know how many of you remember like using your old video game console, your Atari 2600 or your Pong machine plugged into your TV. Once in a while if you're using that and then like your sister picks up the cordless phone or whatever, you might see some interference on the screen, and that's EMI. Most of the time it's just annoying, but it turns out that the EMI, the emissions emitted from the device, could be monitored and possibly used by an attacker to determine information. Some of that might be known as tempest monitoring, if people are familiar with that, which was discovered by Wim van Eck in the Netherlands, I believe, a bunch of years ago, which basically allowed somebody to monitor the EMI coming off of a computer monitor with a receiver and then view the data that's being viewed on the screen. So, especially with monitors that are using such high voltages on the CRTs and everything, possible to do that. The other thing here, as far as emissions, the opposite of that is immunity, meaning that devices could also be susceptible to RF and to electrostatic discharge that could be intentionally injected to cause failure. And that's something, a lot of times with immunity types of attacks, if you are using ESD, it's usually an unpredictable type of thing. So if an attacker is taking an ESD probe and trying to zap your device to see what it does through the keypad or through any sort of external interface, it's hard to control the ESD enough to give you a repeatable attack, but it could physically destroy the device if that's their goal.
Have you done any research with RFID tags? And where, in essence, is a mission, you go through a gate or something like that,
Right.
and it sets it up. However, you could be a passive listener waiting for someone to come through a gate, and since it does set it off, I'm sure there's a certain emission from that RFID that's going to go out to a certain point, and which means you don't have to actually be the one setting that tag to tell it. You can just be a listener.
Right. The question is what about RFID stuff where the tag is intentionally transmitting stuff as you walk through a detector? And yeah, those are powered by something called parasitic power, and your RFID tag doesn't have batteries in it. It walks through, when you walk through your security gate or whatever, there are big antennas in there that are transmitting RF that's being converted into electrical power to power your device to transmit back. So the transmit range of RFID varies, but it's really close range. I mean, it's usually maybe a meter or less. So if somebody was monitoring that, they'd have to probably be pretty undercover, or else it would be pretty obvious that someone's trying to read that data. But yeah, it's totally possible. Another version of that would be maybe an attacker could just create their own antenna system that would enable your RFID to talk back to me. So yeah, that's emissions. That's a perfect example of emissions is RFID, or any sort of wireless. Aside from security, the EMI emissions and immunity are part of a lot of specifications. So if you are designing a product, say a medical product or any sort of consumer product, you need to limit emissions anyway. It would be nice if some of these specifications included security in there, but their main reason for doing it is so your device doesn't interfere with the television, or doesn't interfere with cordless phones or other products. So it's sort of a byproduct of reducing immunity and emissions for products is you get a little bit of security there as well. The best way to do that would be to install EMI shielding on your device, which is either through coatings, tapes, specialized enclosures that are specialized, I guess, envelopes that you put over enclosures or over circuitry that will help decrease emissions and also increase the immunity against RF and ESD. I don't know if any of you have heard of like high energy RF, HERF guns is something that people have experimented with, that are devices that would create huge blasts of RF energy that would basically render a device inoperable. So if you have EMI shielding, maybe you'll be prevented against that a little bit, depending on how high-powered the RF emissions are. The problem is if you are using EMI shielding, be aware of any changes of the thermal characteristics in your device, especially if you have something that runs hot. You need to make sure that you don't totally change the characteristics of that if that is something you need to keep within a specification. Any questions on any other housing type of level stuff before we go into circuitry? Okay. Now this is my favorite area, is circuitry. I like being able to physically touch devices and change things around and see what's going on at the circuit level, so this is the exciting part. There's a bunch of different things that can be done at the circuit board level, and we'll go through all of these. The first and most important for an attacker anyway is gaining physical access to components and physical access to circuitry. If an attacker does have access to components, it makes it really easy for them to reverse engineer the product. Basically, any components that are available, they can be reverse engineered, and the attacker can go and look up the data sheet on Google or any manufacturer's website, figure out what those devices are doing, and then put together a pretty good idea of how the device is operating at a high level, and then what sort of attacks they can take against that product. So suggestions here is obviously make any of the sensitive components difficult to access, place them in areas that are a pain in the ass to get to, whether they're on the opposite side of a board, maybe close to an area that will prevent them from accessing or probing or figuring out what they are. Another thing is removing identifiers and markings from the ICs. So as you most know, if you look at a circuit board, each device tells you what the part number is, when it was manufactured, what the company is, which is excellent information for an attacker. So removing that information makes it a lot harder for an attacker to figure out what the device is, which is known as demarking or blacktopping. That's basically just removing that information. There's a number of ways to do it. There's third-party vendors that can do it. You could also do it yourself in-house, either with Dremel tool, laser etch, or all sorts of things. So if you do have the identifiers and the markings removed, it is sort of obfuscation, right? Because you're not really protecting anything, you're just preventing somebody from figuring out what it is. The thing is, aside from an attacker saying, okay, this is the processor, this is flash, this is RAM, that can only get them so far without knowing the pinouts, without knowing specific functionality of each device. So it will definitely increase difficulty to a level where it will turn off a lot of people. And I'll say that from experience. Because there are still ways, even if somebody doesn't know what the devices are, say in this case, you can't really see these numbers on the picture, we know this is a processor, we know that's flash, and that's probably SRAM. So, I mean, we could try to monitor some of the lines between here and probe things and figure it out, but it increases difficulty. Another thing you can do is use some advanced packaging types where they're harder for an attacker to probe. Instead of using surface mount parts like, or either dip parts like standard through-hole components, or using non-fine pitch devices like SOIC devices, which is a footprint here. Use other stuff like BGA, which is a ball grid array where all of the pins are actually balls underneath the device. So an attacker can't probe the size of the device. They have to basically get underneath, and that's hard without the proper equipment. COB, chip on board, is another example, which is basically the actual die of the device wire bonded directly to the board, so there's no plastic packaging there. And here's an example of that on a device. So it's just the die is underneath, and it's coated with this epoxy glob, which is one of the tamper mechanisms. And then using epoxy encapsulation on the critical areas will prevent the probing and somebody from easily removing the device and figuring out what it is. Maybe if it's a flash device, it will prevent them from removing it, reading the contents of it. The only problem here is make sure that if you are using encapsulation, understand what you're using it for. This is an example, another USB token that I talk about later today, is they had their memory device, which is a serial EEPROM, covered by this epoxy here, but then this footprint's wide open, which is for some memory expansion. And the problem with serial EEPROMs is it's a serial interface to 2 or 3 wires. So those wires that I use to communicate with this device are accessible out here. So I don't even need to worry about the epoxy. I just solder wires onto there and then use a device programmer and read the information out. So this vendor actually learned the hard way, and then they fixed the problem. And actually in this case anyway, even if these pads weren't here, you could just take an X-Acto knife, scratch off where you know the pins are, clip onto those pins, and then read the device. So PC board design and routing. Remove unnecessary test points. If you don't need test points, don't use them. If you do need test points for manufacturing or whatever, use a filled pad as opposed to a through-hole one, because that will reduce some of the EMI emissions. Obfuscate trace paths if you have to prevent easy reverse engineering. It's something I wouldn't normally recommend, just because it's obfuscation and somebody can still figure out what it is. But hiding critical traces on inner board layers, making them harder or impossible to probe, is something that would be useful, especially if you have traces going between 2 BGA devices. The trace will go underneath the circuit board. It can't be accessible at any part along the way. Use buried vias, which would basically connect 2 or more inner layers together of the board, but never bring the trace out to the outer layers. Some other things, standard engineering design types of things, keep the traces as short as possible. That will reduce EMI and will probably make things a little harder to probe. And that sort of goes backwards with what I said about obfuscating trace paths. Because if you obfuscate trace paths that are longer, you might introduce other noise issues. Use properly designed power and ground planes, another way to reduce EMI. Noisy power supply things. Basically, the more EMI you can prevent from being transmitted, the less chance of an attack you have. Bus protection, so any address control lines that you have connecting between memory, make sure those are sufficiently protected underneath the board or hiding them in some way, because a tap board could be used to easily intercept data. And this is a picture from Bunny Huang's book on hacking the Xbox. he created this little monitoring module that sits right over the Xbox's hypertransport bus, monitors the data, figured out that there is a way to load unauthorized code onto the device. So the hypertransport bus is this high-speed serial bus, and he just basically just monitored what was going on, slowed it down enough where you could analyze it on a logic analyzer. So be aware of any of the data that's going across any of your critical lines and protect them as necessary. Memory devices, another area that most any embedded system is going to need memory on board, whether it's external to the processor, whether it's on the processor. Most memory is notoriously insecure. There's not a lot of memory devices that have specific security mechanisms other than like a standard boot block lock area for bootloaders and things like that. Serial EEPROMs, as I mentioned, they can be read in circuit. They're notoriously insecure. RAM devices, I also mentioned this, retain contents after you move power, so there is some burn-in problems there. Security fuses, boot block protection. I'd say use any security mechanisms on the device if they're offered. A lot of flash devices do have the boot block lock. They do have password protected areas that you need to access with a password where the timing for those are slowed down so you can't do a brute force attack against it. The thing is that they can be bypassed with dye-analysis attacks using focused ion beams. I don't get into that here. If you happen to come to DEF CON on Friday, I do talk some details about analyzing dyes to retrieve information, and there's a link to some information as well. If you do have security fuses, here's an example here of an attack where the security bit can be removed by fluctuating VCC on the programming line. So in that case, a user of the product might think they're secure, and then somebody finds this problem. They attack the device, remove the security fuse, now they have access to read the firmware right out of it. Programmable logic, another form of memory. In most cases today, a lot of people are using PLDs or FPGAs in order for their algorithm-specific things or product-specific IP. SRAM-based FPGAs are the most vulnerable to an attack because you need to use an external serial EEPROM or some sort of external memory to load configuration into the device. The bit stream between the external memory and the FPGA can be monitored and then cloned. So there are some new devices that you can use in place, Actel Antifuse and QuickLogic FPGA, that actually have some security designed into them. If you are using programmable logic, protect against IO scan attacks where somebody would essentially brute force your device to figure out all of the different combinations of inputs and outputs. And then use any of the unused pins you have on the device maybe to detect probing, use as a tamper detection, so keep the line pulled high, and if an attacker pulls that pin low, if they're probing it, you'll know that that pin is never supposed to be pulled to ground, perform some sort of action based on that. Add digital watermarks, something that identifies that the IP in there is specifically yours. And if you're using a state machine of any kind, just make sure that all your conditions are covered, so if you do enter an unknown state, your machine will fail safely and shut down in some way. For power supply, most devices again will have some sort of power supply. Define your minimum and maximum operating limits, meaning most devices are only supposed to run on a particular set of voltages. Keep it that way using watchdogs, using supervisory circuitry. If your device goes above or below its standard voltage ratings, do something based on that, or at least prevent that from happening using like a linear regulator, a DC-DC converter or something. That way, if an attacker is trying to vary the voltage in order to get some sort of unintentional operation, it won't happen. Also compartmentalize your noisy circuitry, which is normally in your power supply area, to reduce EMI. Here are some examples of monitoring the power supply, current fluctuations to determine crypto operations and determine crypto keys and processor operation and things like that. So it is possible to do SPA and DPA, and there is a link to some countermeasures against those two things. There are some references in the back as well. Clock and timing, another thing that is possible for attack, which would be an attacker changing or measuring timing characteristics of the system in order to gain some sort of information, crypto keys, passwords, whatever. Active timing attacks would be an invasive attack where an attacker would vary the clock of your system, maybe to speed it up or slow it down in a way to gain more information. So say if you have a time-based token, that was running on a specific time base, if you speed that up, you might be able to get more one-time passwords back enough where then you could maybe analyze how those passwords are being created and then figure out what the algorithm is and work backwards from there. Passive timing attack is similar to monitoring EMI or monitoring power supply fluctuations, is monitoring timing of computations and of events to try to figure out certain things. Different tasks take different amount of time, especially crypto operations are very time intensive. I/O ports on your devices. Any unused I/O pins should be disabled or set to a fixed state, or as I mentioned with FPGAs or PLDs, use them to detect probing. The problem with that is if you are using them to detect probing, they could introduce unwanted noise unless you pull them to a known state, but that is something you can do. If they're unused anyway, you might as well use them for a security purpose. Prevent against ESD on exposed lines, so on keypads, buttons, switches, anything external to the user, prevent that against electrostatic discharge, which would prevent your device from going into some unintended state. Crypto processors using any sort of encryption algorithms, as you know, the strength of the crypto relies on the secrecy of the key, not the algorithm. So even if somebody knows what algorithm you're using, it doesn't really matter. So what you need to focus on is protecting your key. Depending on your product, there's a number of different stages you can do. This also goes without saying is it's not safe to assume that a large key size will guarantee security. A lot of products say we use 1024-bit blah 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 blah. But if your security isn't, if your crypto isn't implemented properly, or your keys aren't stored properly, it doesn't matter how big it is. If an attacker can get access to that, then your crypto system is going to fail. So that's what I mentioned. The next thing. Definitely, if you are using crypto, test your implementations in your laboratory. Try to break the product first before your marketing team goes out and says that the product is secure. Along with that is don't roll your own crypto. This is probably the most common problem in engineering and one of the worst problems where companies say, we've created, our scientists have created the #1 unbreakable security encryption in the world, and it's XORs against, something. Because they don't understand the threat, and we do. So, I say that, and it's true in 3 different examples. The Palm OS problem, which I mentioned earlier, USB authentication tokens I talked about tonight, and the iButton, there's a problem with one of the Dallas Semiconductor iButtons. They all use XORs, and they all say, they're unbreakable or whatever. Except Palm actually didn't say that, so I'll give them some credit. The thing is, if you roll your own crypto, it's usually security through obscurity. So don't rely on that. If you are using crypto, move your processes out of firmware, so out of flash ROM, into an FPGA device, into something that's harder to probe, maybe even into an ASIC. And also, if you're moving crypto out of firmware into hardware, it's going to be more efficient because things running in hardware are faster anyway. Or use a secure crypto coprocessor like the IBM 4758. There's a number of different products that are totally self-contained hardware tamper response, really based for security and for protecting crypto information, which is better than probably rolling your own sort of security mechanism. I'm going to run through the firmware really quickly. There's a few steps you can take, though most of them end up being obfuscation types of things. Programming practices, as you know, flaws and bugs are a major cause of security compromises. Buffer overflows, they happen in embedded products, in hardware products, just like they do in software applications, so protect against those. Any functionality you don't need, any debug routines you don't need, remove those from your retail products. An example is the Palm backdoor debug mode, which is referenced here, and it is basically a documented developer's mode that can be used for all sorts of things, but it can also be used for an attacker to gain access to your device. That isn't really necessary for devices that are used by consumers. It's only good for developers. You should have a distinction there. Removing debug symbols and tables is the same thing for the most part when you're compiling code for your product. It's a command line switch, or it's a checkbox to turn that off. Enable optimization as much as possible to maybe create, not only code efficiency, but also maybe obfuscate enough the identifiable code segments. So the more optimized it is in assembly, somebody would really have to pour through and figure out what's going on. Storing secrets, again, this goes along with the crypto. It's hard to erase data, so don't rely on that. And then a solution here, though, is to limit the amount of time that the data is stored in the same region of memory. So if you do have a crypto key, flip bits around, move it around to different locations, and you won't have that burn-in. So when you go to zeroize your memory, you can safely know that no one's going to go and try to analyze your device after the fact. For runtime diagnostics, you might want to make sure your device is fully operational at all times. This goes along with your tamper detection mechanisms. You implement those at this point. You have periodic system checks, make sure everything's okay, checksums of memory or signing of memory to make sure memory hasn't been tampered with. Use some sort of watchdog functionality there. Because if you don't take this into account, if your device fails, it might open itself up to other sorts of attacks. So what you need to do is determine how your product handles failures. Are you going to just set some flags and keep going if it detects a problem? Or are you going to shut down or zeroize memory? Basically, just monitor yourself at all times. Field programmability, which is something that's common in a lot of products these days, is once the device is up there, a vendor will release firmware updates, things that the user can do to update their product. One thing to consider is, are you giving your firmware away to everybody on your website for free? If you are, an attacker can easily get your code, analyze it, and they might not even need a product to figure out what problems there are there. So use some sort of signing or use some sort of hashes, at least to reduce the possibility of loading unauthorized code. It will also verify for the end user that the image hasn't been tampered with somewhere along the way from manufacturer to user. And encrypt firmware images if you can. The challenge here is protecting that key. Again, I mean, hiding the key in any application is hard. And then one other thing too is compression routines are an encryption, and a lot of times companies will say we use encryption to send our binary updates to people, but compression using zip is not encryption. And then the final thing here is obfuscation. Again, security through obscurity doesn't work, but if you want to do certain things that might discourage certain people, you can encode fixed data, scramble address lines. I'm kind of embarrassed saying these things because I wouldn't really do them in my own products, but in certain situations they might be good. Write lousy code I probably wouldn't do. However, adding spurious and meaningless data, signal decoys, is something that is good. You might have an FPGA sending out certain bits on certain pins that aren't doing anything, but an attacker might spend all their time looking at that instead of going somewhere else. So, any questions before conclusions? No? Okay. You guys all just want the shirts, right? So, the most important things for designing secure hardware and designing products in general is determining what you want to protect, what areas you want to protect, why you're protecting it, and who you're protecting it against. Because no one solution fits all. For me, I might design for one of my products. I might only use certain features for somebody else if they have, it's a different product. It has a different set of operational characteristics, so your solution will vary. If somebody comes to you and says they have the best product to secure your hardware, they're probably lying. The best defense is I mentioned this at the beginning too, is make the cost of breaking the system or breaking the product more valuable than the information, or more expensive than the information that the attacker would gain. And also, don't release a product with a plan to implement security, because it usually never happens. Once the product's out there, you can't retrofit stuff. You see it all the time. Microsoft is still trying to figure out how to make their operating system secure. The final thing is think as an attacker would when you're designing your product. Make time to break the product. Do your design, your iterations of design. Try to break it. For a week or for a few days, put yourself in the mind of an attacker and say, okay, what would they do, and try to break it. Because a lot of times you're so focused on getting the product working, you don't realize that you've just introduced all of these problems. So be aware of latest trends, monitor websites, monitor Slashdot, whatever, see what's going on there. Learning from mistakes, easier said than done, is study history, learn about the previous attacks, read up on any areas you can, to make sure you're not either reinventing the wheel or opening up some sort of problem that's already been fixed. And then nothing's ever 100% secure, as we know, and now you know. So I do have a bunch of references in the back, tons of stuff. We are out of time, so thanks for coming. And let's see, we have the books, but any other questions? Yes?
Well, one of the objectives you might have for conclusion is that you might not be worried about someone breaking in that has the knowledge even for an academic. But what you're worried about is someone creating a product that someone can easily use, then to modify their own product, the manufacturing product, to bypass this thing. So if you make it such that, I don't care if an academic gets into it, but if someone can mass produce that
from being easily recreatable for somebody else to use in another attack. Yeah. Right. Yeah, the cable system learned that quickly once they started losing money and everyone was watching Playboy for free. Yeah. Okay, well, people are coming in. I don't know, most of these people probably weren't in the talk, but I don't know what they're coming in here for. Do we have a break in here? I think we have a break next. Oh, okay. All right, so here's what I'm going to do for the shirts. Has anybody read my hardware hacking book that came out in January? Hardware Hacking, Have Fun While Avoiding Your Warranty. Okay. Well, in that case, nobody gets the shirt. I'm going to give the book away to the oldest person in this room. Who's over 50? 2 people? Who's over 60? Who's over 55? How old are you? No, not that old yet. If you want the book, you can come up and get it, because you're probably the oldest. Shirts, if you want, come up and ask me a good question and you'll get one. So, thanks.